Alright, so in this lecture we will start talking about the third chapter, quantum teleportation. So quantum teleportation is a very interesting and a major field in quantum computation and in quantum information. So what's quantum teleportation? Well, it is the process of transferring the state of an arbitrary qubit from one location to another. Okay, so we're transferring the state of a qubit, not the qubit itself, but transferring the state of an arbitrary qubit from one location to another is called quantum teleportation. So this process is heavily based on the use of entanglement of EPR pairs. Okay, so an EPR pair is 1 over square root 2, 0, 0 plus 1 over square root 2, 1, 1. It's called an EPR pair, also called a Bell state. This is one of the Bell states. So this is an entangled state because observing one qubit, and if we assume that the outcome of the first qubit is, say, 0, then the probability of observing the second qubit as 0 is exactly 1. So we will use this entanglement property in quantum communication. And in fact, this quantum correlation can remain even if the qubits are separated from each other light years away. So this correlation plays an important role in quantum communication protocols. Now, the first result that I would like to talk about is something that has to do with quantum information theory. And it's a well-known theorem called the null cloning theorem. Null cloning theorem tells us that we cannot copy an arbitrary quantum states. Okay. So first we have to define what we mean by making a copy. Okay. So this can be expressed by hypothetical quantum copy machines. So let's give a definition first. Okay, so suppose that we have a set of orthonormal bases. Call them A1, A2, up to AN. Okay, and let's denote the state space by Hn, and let's denote suppose that Hn denotes the state space, and suppose that we have a reserved state, and let's assume that it's A1. This reserved state is called a blank sheet state, okay? Now, we say that a unitary mapping in Hn tensor Hn is called a quantum copy machine if for any state psi u of psi a1 equals psi psi. So a quantum copy machine is a unitary transformation which takes two qubits psi and the blank sheet state a1, and it copies psi over a1. Okay, so the null cloning theorem states that for n larger than 1, there is no quantum copy machine. There is no such U. Okay, so let's shortly prove this. Now, the proof relies on the linearity property of U and having different descriptions of tensor products. Suppose that we have a quantum copy machine U, okay, for n greater than 1. So that means we have at least two orthogonal states, A1 and A2. So it follows that we should have in this case we should have that U A1 A1 is simply equal to A1 A1. It copies A1 over A1, okay, assuming that A1 is the blank sheet state. And U of A2 A1 is equal to A2 A2. So it copies A2 over the blank sheet state A1. But suppose that we have a suppose that we want to copy a superposition. Okay. Now, if we let the input qubit, if we let the first qubit of U to be a superposition of A1 and A2, then U of 1 over square root 2 A1 plus A2 okay, and the second qubit is A1, the blank sheet state. So if you want to copy the superposition state over A1, then we want this to behave like we expect that it should output 1 over square root 2 A1 plus A2, right? Tensor, the second qubit will be 1 over square root 2 A1 plus A2. Okay, and if we distribute this, this is equal to 1 over 2 A1 A1 plus A1 A2 plus A2 A1 and plus A2 A2. Okay, but since U is linear, well, this expression should also be equal to, so this should also be equal to 1 over square root 2. You will distribute inside. Okay. And then we will have 1 over square root 2 U of ket A1 A1. Okay. Plus 1 over square root 2 U of A2 A1. So evaluating these two expressions, this will be equal to 1 over square root 2. We have a copy of a1 over a1, so we have a1 plus 1 over square root 2 u, and we're copying a2 over a1. We have a2. Right, so we have two different representations for this, but this doesn't coincide the definition of a tensor product. Okay, so we have a contradiction. So then it follows that there cannot exist a quantum copy machine of this kind. Okay, so this is called the null cloning theorem. And there's a similar theorem for deletion, in fact. The time reverse dual of the null cloning theorem, so to speak, and it's called the null deleting theorem. We're not going to prove this, but the proof is in the lecture notes, so I'm just going to state it. So this is by Patty and Braunstein. This was proved in 2000. So it says that if we have an unknown quantum state psi, okay, then there is no linear isometric transformation isometric means geometry preserving. Such that so given two copies of psi, okay, and some ancilla bits, there's no isometric transformation which maps these 3 qubits to psi, some blank state sigma, and a prime, with the final state of the ancilla being independent of psi. Okay, so there is no such transformation. This is called the null deleting theorem. It can be considered as a time reversed dual of the null cloning theorem. Okay, so there is no, it's more like a reversible uncopying of an unknown quantum state. Okay, so this is not kind of a deletion. It's not a deletion procedure as in the classical irreversible sense, but it's more like a reversible uncopying. Okay, all right. So these two theorems are well-known theorems in quantum information theory. So next thing to consider is how we actually transfer the state of a qubit from one location to another. Now I'm going to explain the teleportation protocol. Okay, so suppose that we have two communicating parties, Alice and Bob, as usual. And suppose Alice wants to send an arbitrary qubit to Bob. So she has a single qubit state in Alice wants to send her qubit to Bob. So that's our goal, okay? So Alice's state is assume that it's for some A and B, A0 plus B1. Okay, so this is Alice's state. Okay, so this is actually unknown to Alice. Alice doesn't measure her state, and she wants to send this state to Bob. Now, so how many ways can we send this? So if there's a quantum channel between Alice and Bob, quantum channel meaning that if Alice can send Bob the whole qubit, okay, as a quantum state, then we say that there's a quantum channel. Okay, then there should be no problem. Alice can just send the entire qubit to Bob, and Bob will receive the same qubit. And if this is not possible, then what we are left is a classical channel. Classical channel is an information channel through which we can send classical bits. Okay. So we assume that there is no quantum channel between Alice and Bob. That would be too much luxury. Okay. But we assume that there is a classical channel between them. So Alice can send classical bits to Bob. Okay. Now, Alice cannot measure her state because it would disturb her qubit. Okay, then we have an information loss in this case, so she cannot do that. Also, she cannot make copies of her qubit. Okay, and have many observations over her qubits, because this is not possible, because copying an arbitrary quantum state is not possible due to the null cloning theorem. So the only possible way for Alice to send her qubit to Bob is by using a classical channel and sending classical bits. And she will actually send 2 classical bits, but she will encode these bits in such a way that Bob will receive 1 qubit. Okay, so that's the idea behind the teleportation protocol. But the way we do this is by sharing an EPR pair between Alice and Bob. So Alice and Bob initially shares an EPR pair. Okay. What's an EPR pair? As we stated, it's 1 over square root 2, 0, 0, 1 over square root 2, 1, 1. Okay. So let's suppose that the first qubit belongs to Alice. So the first qubit. And the second qubit belongs to Bob. Okay. All right. And then Alice also has her own qubit that she wants to send. All right. Now the compound state, the 3-qubit system, will be then, so we have Alice's original qubit, A0 plus B1, and then we have the EPR pair. Right? And if we distribute this, what we get is a 3-qubit state. So this is equal to A over square root 2, 0, 0, 0, plus A over square root 2, 0, 1, 1, plus B over square root 2, 1, 0, 0, plus B over square root 2, 1, 1, 1. Okay. Now only the third bit belongs to Bob. This is a 3-qubit compound system, and these the first 2 qubits here, these belong to Alice. Okay? So Alice can access the first 2 qubits only. Now the protocol starts with Alice performing C0 transformation on her qubits, using the first qubit as the control qubit and using the second qubit as a target qubit. Okay, so first step, Alice performs C0 on her qubits. After applying the C0, this state will become A over square root 2, 0, 0, 0, so nothing changed with the first expression. Square root 2, 0, 1, 1, nothing changes here. And here we have 1, 1, 0. We flip the second qubit because the control qubit is 1. And we have finally b over square root 2, 1, 0, 1. Okay. Next stage is that Alice now applies the Hadamard transformation on the first qubit. Okay, so the result will be so we have a over square root 2, and then we have 1 over square root 2, 0, 1, and then the second qubit and the third qubit they don't change, plus a over square root 2, 1 over square root 2, 0 plus 1, 1, 1, okay, and plus b over square root 2 times 1 over square root 2, 0 plus 1, 1, 0. Okay, so we are here now. And then finally, we're going to write b over square root 2 times 1 over square root 2. Sorry, this should be minus, okay, because Hadamard 1 is 0 minus 1. So this should be minus. And then similarly, we have 0 minus 1, 0, 1. And if we distribute this, this is equal to a over square root 2, 0, 0, 0, plus, sorry, a over 2. And then we have a over 2, 1, 0, 0, plus a over 2, 0, 1, 1, plus a over 2, 1, 1, and plus b over 2, 0, 1, 0, minus b over 2, 1, 1, 0, plus b over 2, 0, 0, 1, and finally minus b over 2, 1, 0, 1. Okay. And we can take Bob's qubit apart. This can be rewritten as 1 over 2, 0, 0, a0, plus 1 over 2, 1, 0, a0, plus 1 over 2, 0, 1, a1, plus 1 over 2, 1, 1, a1, and then plus 1 over 2, 0, 1, b0, minus 1 over 2, 1, 1, b0, plus 1 over 2, 0, 0, b1, and minus 1 over 2, 1, 0, b1. And then we can take a0 plus b1 parentheses, and a1, b0 parentheses, and a0 minus b1 parentheses, and also a1 minus b0 parentheses. So this will be equal to, in 1 over 2, 0, 0 parentheses, we have a0 plus b1 plus 1 over 2, 0, 1, a1 plus b0 plus 1 over 2, 1, 0, a0 minus b1 plus 1 over 2, 1, 1, a1 minus b0. Okay, so the last qubit belongs to Bob, and the first 2 qubits belong to Alice. Now Alice observes her 2 qubits, okay? Now in the outcome, she either sees 0, 0, or 0, 1, or 1, 0, or 1, 1, each with probability 1 over 4, right? Okay, so let's draw a table. If Alice observes Alice's observation and post-observation states, now if Alice observes 0, 0, then the new state of the system is 0, 0, a0 plus b1. If Alice observes 1, 0, 1, then new state will be 0, 1, and the third qubit will be a1 plus b0. If Alice observes 1, 0, new state will be 1, 0, a0 minus b1. Finally, if Alice observes 1, 1, then we have 1, 1, a1 minus b0. Okay, so the first 2 qubits again belong to Alice, and the third qubit belongs to Bob. Okay. Now, Alice sends Bob her observation results, which is just classical 2 classical bits, right? So through the classical channel, Alice sends these 2 classical bits to Bob, and then Bob performs the following. So Alice sends her 2-bit observation results. Two-bit observation results. Okay, so now Bob has 2 classical bits, okay, and he has his own qubit. Now, if Alice's bits are 0, 0, Bob doesn't do anything with his state, because this is already the state that Alice wanted to send originally, right? So if Alice sends her 0, 0, then Bob is in state A0 plus B1, so Bob does nothing. Okay? So if Bob receives 0, 0, he does nothing. If Bob receives 0, 1, then Bob is in state A1 plus B0. And how do we obtain A0 plus B1 from Bob's state? Well, all Bob has to do is to perform NOT gate, right? He applies NOT gate. If we apply NOT gate on A1 plus B0, then the outcome will be A0 plus B1. So again, in this case, we obtain Alice's original qubit. If Bob receives 1, 0, then he performs the phase flip gate. He applies the Z gate. Right? We just have to change the sign in this case. And that's done by Z gates. If Alice sends 1, 1, then Bob performs, he first applies NOT, and then Z. So you apply the NOT transformation, and then you apply the Z transformation. Okay. So this is how a quantum teleportation protocol works, okay? And we should note that we don't transfer the qubit itself from Alice to Bob. We just transfer the state of the qubit instead, okay? And as soon as Alice, the original state held by Alice is destroyed in the protocol as soon as she measures her qubits. Okay, so next we will talk about superdense coding.